Yeah, yeah.
Good.
Okay. Our second speaker today is David Kelf from Breker Verification Systems, where he is CEO. His talk today is on automated SoC performance and power profiling, pre and post fabrication. Dave is a well-known EDA industry participant, having run Cadence's verification marketing, driven Synopsys verification strategy, and run marketing for Co-Design, System Verilog, Novas, Verdi, and others. Now he is the CEO at Breker, focused on PSS-based SoC verification. He has a solid engineering background, has performed many ASICs designs, and holds a microelectronics MSc from Brunel University. He's currently located in Boston, in the USA. Over to you. Thanks, David.
Great. Thanks, Mike. Actually, I'm in Bath, UK right now, which is great. Okay. So very convenient for this. So I was fascinated when I saw this subject of this DV Club coming up, because this is something that Breker has been doing a lot of work on, exactly this subject, with a number of the leading processor and systems companies in the industry. And so what we thought we would do is talk about that and talk about the work we've been doing, and try and discuss some of the automated solutions that we're trying to come up with actually for the discussion that Nick so beautifully presented. So I appreciate what Nick said. In fact, if I show my first slide here, if I can, basically this exactly agrees with Nick's analysis of what's going on today in the market. So, you know, in the past, right, we would be working with simple SoCs like the one you see on the screen here, and we would have issues and bottlenecks and problems of that SoC, which would basically become a bug if we found that it started to create hazards as we were reading and writing across the device. But now what we're looking at is devices like this, which is Intel's Meteor Lake, and it's exactly the kind of device that Nick was describing in his presentation, where now we're dealing with die-to-die interfacing using interfaces like UCIe, and even within those dies, you know, the complexity and the data transfer is incredibly complex, and needs a lot more analysis to figure out, you know, can we avoid the kind of bottlenecks that are going to really trip up these devices? So that is what all this is about, and what a number of companies have been working with Breker on is how can we automate the testing around that, so that instead of trying to manually predict bottlenecks and corner cases that might crop up in these incredibly complex devices, you know, is there some automated method that would allow us to discover those and sort of do a much better job of finding them. So if we look at the kind of solution that Breker and others are working on, it's essentially a synthesis solution for generating test content. And if you look at the Breker system, there's really two major parts to it. The first is a synthesis process that takes abstract models that could be written in C++ or PSS, or be represented by system VIP, as we put it, modules. And then there's a second part, which we call the synthesizable verification OS. And what this does is it provides a lot of OS-style capability, which we need to actually do this kind of performance analysis, including scheduling concurrent tests, you know, allocating resources such as memory, interface units and stuff, and providing portability from simulation, emulation, and right down to post-silicon, where all this needs to be done. So what I'm going to do is just run through a straightforward example using that initial SoC of how we're kind of tackling this with some of these companies, and then we'll show how it scales up to some of these large devices. So if we look at a simple little SoC like this, you can imagine creating a test where, you know, maybe we take an image, run it for an SD card controller, the memory, we do some processing on it, and we put it out for a display controller. So you could come up, as Nick put it, with a graphical kind of representation of this scenario, and we can provide a lot of testing. Hey, Mike, I don't know about generally, but I'm getting a bit of noise, typing noise on my, I don't know if there's a mute or someone needs to be muted. Okay, thanks. So, so we can come up with a graphical representation of these scenarios. And of course, these graphical representations can be hierarchical. So within that, we can get into a fairly detailed level of some of the the individual operations and the clock cycles they will take at this sort of higher abstract level. Having done this, what we're able to do is generate tests in a number of different ways. So let me take that simple situation, and let's assume we're just going to generate one straightforward serial test, which we could just do like this. If we do this, that's pretty nice, but it's only just basically doing a simple functional test of that design. We could spread this test across several of these CPUs or threads on the CPUs like this. So where we have multiple CPUs actually trying to perform this test and spreading it across the whole system, essentially. We can also take this and we can start to bring in some of the resources. So obviously, when you're moving images around, you're using memory. So you might allocate some memory regions, and then what you'd do is the first part of the operation would probably take this JPEG image, put it into memory. The photo processor would then process it into the display required, and that would be put out through the display controller. So, a pretty simple, straightforward test that makes use of this, straightforward SoC here. Okay. Now, if we were to take this a stage further, what we might want to do is take the same SoC, but now create a graph that tests across all of these different IP blocks on this SoC. And you can imagine all these different paths for transferring control and data through all these scenarios. And once again, we could do a single test, that first scenario, the same one as we showed last time. And we might do a second one where the camera is loading data through an SD card controller, okay? So this, again, nice, simple functional tests, one after the other, very straightforward. However, what we really want to be doing is doing all this concurrently. So across these different threads, we could take our first test, as we did last time, and spread it across 3 threads. But we could take the second test and operate it concurrently, making use of the resources, depending on the number of resources that are available, one after the other. So here you can see we've got a camera read going on, making use of the photo processor and putting it out on SD card controller writes, concurrently with that first test we had, taking a SD card image and putting it out on a display controller. Okay. And we can actually take this further, because every one of those paths in that straightforward high-level graph need to be exercised. So we might add another test, and another test. And now you can start to get a sense that here we can build up a whole set of concurrent tests and spread it across this SoC and operate them at the same time. And so what we're doing as we're moving a large amount of data around these fabrics inside this system is we're starting to stress test, as Nick put it, the whole entire system and starting to look for bottlenecks. If we start to think about resources, so I look at my same 2 tests and how they're spread around, now I might want to allocate some memory as I did before for the first one of these tests. And then as I start to operate the second test, I might want to reallocate memory to allow some memory regions to handle the images from the second test. And as we say in Breker, we have the worst memory allocator in the world. So we purposely try and allocate memory that's going to allow memory to stomp on each other. So what we can do now is actually see if we can stress test the resources that are available in the system as well. And again, this is still a very simple test, but you can imagine if I was to multiply and scale this up, we can start to really stress test the memory system. We can start to create coherency type issues that are going to occur. We can start to stress test it to find hazards with the reading and writing register files and so on and so on. So this, if you like, is the basic idea behind what we're trying to do at a very simple level. Now, so this is nice, but so far we just talked about sort of random testing and how we can try and randomize and build up a set of tests that might stress test and trip over areas in the design which might reveal corner cases that we can't predict by hand. Question is can we control this in some better fashion? So if we go back to how the test synthesis system and the verification OS works, what we're doing essentially is taking this high-level graph of these scenarios, which of course is hierarchical, so under each one of these boxes we have much more detailed scenario descriptions. And what the synthesis and verification OS does is it essentially flattens out this graph, performs randomization, and does a number of other processing to essentially create this tree-like structure that you can see here in this image. And what we're doing then is creating a tree, and then we're walking each path of this tree to create our individual tests. Okay. Now, what you can see here is actually a coverage map built on top of this tree, where the red areas are the ones that are hard to reach, the light green are the ones that are reached very often, and the dark green are the ones maybe reached once in a while. So what we can do is we can look at this image and we can identify, and we can do this automatically, so the system can identify areas that might be using the same resources. So for example, the fast fabric, like the Northbridge bus, could be being used by all these individual branches. And what we can do is we can start to do some coverage analysis to sort of see if we can link up all these uses of a fabric, for example, and put them so they'll actually occur at the same time. So we can automatically start to really stress test the design and apply some fairly powerful coverage rules. And so when we do this, and then we generate this test, we can move these tests around based on this usage of resources. And this is where it gets particularly interesting for larger tests, because now what we're able to do is stress test, different parts of the SoC and try and figure out, where might those corner cases lurk if we find choke points, throttle points, as Nick put it, bottlenecks around the system, or maybe overloading memory usage, reading and writing to the same registers over and over again, and so on. And this is where these SoC bugs really start to occur, when we need to shake them out. So we have a term which we've talked about within Breker and with some of our customers called 3D, three-dimensional coverage. So I'd like to just quickly touch on here. First level of coverage is what we all know and love, combinatorial coverage, where we might be looking at one particular IP blocks, for example, and making sure that we have a cover group that's being fully evaluated within that IP block. So this is a classic UVM type of coverage. We extend this looking in a temporal fashion at sequential coverage to make sure that we have specific sequences of operations or activities or actions that we might want to make sure occur in the system. So we term this sequential coverage, and basically we go through the system in these scenarios and we make sure that all the critical coverage paths which occur over time are actually exercised. So this could be, for example, a state machine, making sure we go through all the individual states, and all the full sort of state machine is being rung out, for example, or it could be a data path or whatever. But then the particularly interesting one for this performance analysis is concurrent. Oh, I should point out that we can, of course, set constraints on these paths and make sure that we actually hit specific coverage points in a sequential fashion. But as I said, the most interesting, of course, is the concurrent coverage idea. And here what we're trying to do is check that, as we said before, certain areas are being concurrently tested. So are you stress testing the fabric by running a number of operations across it, for example? Are you stress testing the memory subsystem? Are you checking coherency in certain areas? That kind of thing. And this is, the idea of concurrent coverage that we can actually set up using a system like this. And while we're talking about coverage, we also should bring up the fact of debug and profiling, which also has to be in 3 dimensions as well. So now we need to look at debug across 3 dimensions, and we need to be able to profile the performance of the design in general to make sure that it doesn't have the kind of bottlenecks that we're talking about. And I'll talk about in a sec. Okay. In fact, let me look at the this debug window here. So Nick actually mentioned this idea of graphically analyzing what is going on in the scenarios and actually being able to look at a full set of concurrent parallel threads at the same time. And here you see a debug window, and on the left top corner there are all the different threads occurring at the same time with their dependencies. And in fact, we can see that there's a number that finished, there's one that's failed, which is red, and so these are all self-checking tests that we can go and test. What we also need to be doing is making sure like the memory map in the SoC or across the different memories is tested, and we can do that. And we can look, of course, at the test source, which in this case is C code, but it could be transactions, and the execution log too. So we need this kind of a debug view in 3 dimensions to actually see what is going on, and also tie it in, of course, with signal level debug such as Verdi from Synopsys. Now, if we have a view like this, we can do quite a lot more analysis to actually profile the design. So if we look at how these tests are scheduled before execution, we can see a number of tests, and in this case, they're all the same size, same number of clock cycles, in fact. What we want to do is recheck these tests after the execution on the DUT, and resize them so they represent the number of clock cycles the test has taken after execution. And you can see here that some of these tests are still fairly big, like this DMA test across here, but they're being driven by small tests, which in this case for some reason has failed, but it's a very short test. It takes a very small number of clock cycles. And what happens here is the whole debugging window adjusts itself so you can very easily see bottlenecks in the system. A white space, for example, like this is a thread that before was actually covered in tests. So you can see there's a blockage that's creating this kind of problem. You can see dependencies that might now not be being met because tests are too late, for example, here. And so we start to get a sense of a visual representation of all the bottlenecks and the bugs that they might cause in a system like this. Again, this is, I'm using a very straightforward SoC here, very simple system, but this scales very well to very much larger systems. Nick mentioned coherency. And of course, as we start to look at chiplets, as my first slide, and we start to look at interfacing between chiplets with standards like UCIe, UCIe is a coherent interface, which is absolutely critical, on these kinds of designs where we're shoving coherent data around and we need to do snoops and various other things across the interfaces. The problem with the interfacing between chiplets, of course, is the latency between them starts to become a factor. And we need to make sure that the coherency is not affected by that as you start to read and write to memory systems across UCIe. So Breker has a number of system VIP blocks. One of our most successful is this system coherency app, which is in use in something like 30 or so larger companies now. And the coherency app, if you look at this graph on the right-hand corner here, contains a number of different algorithms for actually testing different aspects of coherency across a large complex system. And the two windows lower down here, this is actually an ARM window. It actually came from Carbon Design, which is a cycle summation company that ARM acquired many years ago, and they use their windows as a way to graphically represent traffic on buses and in coherency. And you can see the difference that can be achieved by a manual test, which is on the left-hand side, directed testing, to try and figure out where coherency issues might exist along a large complex SoC versus what can be achieved with an automated solution that takes standard coherency algorithms such as the Breker algorithm and saturates the bus and the memory subsystem with address calls and reads and writes to identify where those coherency goals and coherency issues might exist. So this is a very typical kind of cache coherency automated solution that actually allows for corner cases, which the person coding up manually this system on the left, would have trouble with, but it can actually find it on the right by saturating all the tests and looking for these bottlenecks. So this is a good example of a scaling of the discussion we had in the last few slides to actually show what this might look like on a real system, ARM-based in this case. And the other nice thing, we can code this up in portable stimulus or in C++. And in the case of portable stimulus, the same tests, having been checked out on a simulator or an emulator, can be passed to post-silicon. So having made sure that the the pre-silicon design is apparently behaving correctly, we can revalidate it post-silicon using that same debug window and debug mechanism on the actual final silicon, and that final silicon be made up of several dies in a package in a chiplet kind of format. And we can actually run all the same tests and make sure that the same coherency, the same hazards, and what have you are still valid. Okay, so just to summarize then, basically the Breker solution here, which is in use right now for performance analysis, I would say at about 7 or 8 of the larger semiconductor companies today, essentially uses a synthesis approach to generate test content. So we use a synthesis algorithm to generate individual tests, and these are self-checking tests that also contain coverage and debug models. But then we have this extra interesting block we call the synthesizable verification OS. And what this does is schedule the test to create this concurrent coverage type of mechanism to really see if we can hone in on complex fabric type issues, memory subsystem issues, and so on. And these have become particularly relevant as we start to work this at the chiplet level, working across the UCIe interface. And it's possible, especially using both portable stimulus and C++, to create libraries of system VIP to check preconditioned scenarios. So cache coherency being an obvious one, power domain switching, security is now becoming more and more important, and so on, a whole range of these system VIP blocks to do this. So this is the end of my presentation, and I'll be happy also to take questions, Mike, if we have any.
Thanks, Dave. Thank you very much. Finishing on time as well. So we do have some time for questions. The first question I've got is the coherency test intrusive or not?
Intrusive. So, well, you can run it alongside regular tests very easily. The way it works is we generate C code that goes in the processor and some transactions that would go on the I/O. So if you're testing, for example, one chiplet, you might generate some UCIe transactions. And this can run alongside a regular set of tests. So the way it works is the tests are loaded into parts of the memory that's set up for control instructions, so it doesn't interfere with the data instructions, then operates on the processor and attempts to find coherency issues. So I would say it's not intrusive. If you want to make it intrusive, if you want it to intrude on like functional tests that are operating, you can certainly do that. And that can actually create even more interesting scenarios, as you can imagine. But the basic app is, I would say, is not intrusive.
Okay,
if I understand the question correctly.
Yeah, I think you've interpreted it correctly. Thank you. What level of modeling is required to automatically generate these tests in practice?
Yeah, that's a great question. So, so basically, the way a lot of our customers work is they would start with one of these apps, and the coherency app is a common one. And this allows, for the observation of traffic around the system, into the memory, and so on. And then it's very easy to add capability on top of these apps. So if we attack it like that, it's actually quite straightforward to sort of add to the graph, if you like, and build this up. The nice thing about using the apps is you don't have to start with the knowledge of this portable stimulus language, or C++ for that matter. You can build it up as you go along. If you want to start from scratch, building up these tests, then you need to use either C++, which a lot of the folks at the SoC level, including the architects who are trying to come up with the spec for this, are already familiar with. So, all we're doing really is creating these graph models in something like C++. If you want to use portable stimulus, of course, some knowledge of the portable stimulus standard, which is a new standard by Accelera, is required. But it's just to create the graph models and sort of build this up, I would suggest, is not terribly complex, and you don't need to know all the intricacies of portable stimulus to get going.
Okay, thanks, Dave.
Okay.
There's a couple of questions regarding this synthesis. Yeah. So the synthesizable verification OS and the test suite synthesis. People asking if they're just part of the Breker tool and solution. Yes.
Yes. Yeah, they're both part of the main Breker tool. Yeah.
Okay. Thank you. On the concurrency coverage.
Yeah.
Is that just can you actually model that as a normal functional coverage, or can it be generated as for a functional coverage model?
Yes. Another good question. So it certainly can be generated. The way it works is, we generate this tree structure as I showed you, right? And yes. The coverage is sort of overlaps on top of that. So if you just want to look at the coverage that's generated, you can just look at this tree structure and a report that's generated on the side that fits in with UCDB, which is a coverage standard. Yes. And so you can look at that in some of the other coverage tools, such as vManager that Cadence has, and some of the other ones too. So you can look at concurrent coverage like that. You can also set it up. And what's nice about this synthesis tool actually is that this picture here shows is that we can actually drive coverage in as a constraint into the synthesis process. So you can preset the coverage you're looking for as part of the synthesis. And that can be regular functional coverage, it can be sequential coverage, or it can be full-on concurrent coverage. So you can set that up. We use what we call path constraints, which is part of it's not actually part of the PSS standard yet, but it's very aligned with PSS to sort of describe what kind of coverage you require. And then the synthesizer verification, it's a mouthful to say, will make use of that to actually set up these different concurrent operations, trying to sort of create that coverage scenario that you're describing in your path constraints.
Okay, thank you. And one final question: can you visually inspect the profile results to debug the scenario?
Yes. So as I showed you in that previous window, hold on, this one. So this is a visual inspection, but it's a pretty basic one, right? Where you can just see from a number of threads, you can see if, some of these things are turning red because the dependencies aren't met and things like that. You can also do this in a textual fashion using a report, because of course, when these things get much more complex, you need some kind of a text sort of report that can be post-processed, and you can do that there as well. So there's both a text log file report, which describes, concurrency issues that have failed, and also just bottlenecks that might be in the system, or you can do it visually using a window just like this.
Okay. I don't think there's any more questions, so that's perfect. Thank you very much.
Thank you, Mike. Thanks, everyone.
Okay, and we'll be sending those slides and recording in due course. So I think we're going to switch to me now. I'll just share my screen. Oh, maybe that's the wrong one.
Yes, Mike, we are able to see your screen.
Okay, you can see it. Yeah, so thank you for participating today. As we said, the presentations, both slides and recordings, will be available on the DB Club Europe website, which is there, hosted by Tessolve. The PDFs normally go out very quickly, and the recordings about 4 to 5 days. But you'll receive emails about that, and obviously we're adding the answers to the questions asked to Nick Heaton as well. If you've got any ideas, suggestions, topics, just email me. This performance verification one came about as a suggestion from one of our attendees. So we do listen, and then our sponsors respond accordingly. You can also present your own paper. If you've got your own paper that you want to present that you think would be interesting for other members, then feel free to suggest that, but just email me there. So the next one, DV Club, is on the 5th of September, which is about coherency automated verification, and the 28th of November, auto-generation of verification infrastructure for IP to SoC level. So they're the next two talks coming up under DV Club. Again, if you've got a special topic, last year we had 2 talks on OS VVM and UVVM. So we add special topics in as required. The big event coming up is on the 22nd of June, which is our verification futures in the University of Reading. We now have a full program for that, and we have over 400 registrations already. Both you can attend physically in person, or you can attend remotely. We will be sending you a link for that as well. But 22nd of June, and we have about 15 different speakers ranging from formal verification to analog mixed signal verification, etc. for that. And we're also running our first verification futures in the US this year on the 14th of September in Austin. Okay, thank you to our speakers, sponsors, and venue hosts: Agnesis, Cadence, Synopsys, Breker, Impress, ARM, and ST, the venue host, and Tessolve for hosting the event and putting up the slides. So thank you to everybody, and hopefully we'll see you at one of our events coming up. Hopefully, the next one on 22nd of June. That's going to be a big event for the whole day with, I say, 15 plus speakers, including a keynote from ARM talking about safety and security verification, how you can verify a design to be safe and secure. And that's the end. Thank you very much for joining. Thank you. Bye.
Thank you everyone for.
Thanks, Tisha.
Yeah, thank you. Thank you everyone for joining the webinar for today. And the slides will be available today or by tomorrow. Thank you.